Hello and a warm welcome to this presentation. I'm going to talk about our Digital Futures collaborative project, EXTREMUM, Explainable and Ethical Machine Learning for Knowledge Discovery from Medical Data Sources. The project's team is composed of 5 PIs. The main PI is Panagiotis Papapetru, and 4 co-PIs, Lars Oskar, Stanley Greenstein, Christian Rojas, and me, Rami Mushawarab. And this is a collaboration between Stockholm University, KTH, and RISE Research Institutes of Sweden. The motivation of our work is nowadays machine learning algorithms are being more and more applied in diverse domains. And the reason for that is those algorithms provide us with high accuracy for performing certain tasks, and very often they outperform humans. And now within the application domain of health and the medical domain, providing explanations to the predictions made by those algorithms is important and necessary. And the reason for that is the sensitivity of the application. For example, diagnosing a patient with a certain disease. And let's consider machine learning classifiers. So here we would use historical data, and let's take, for example, diagnosing a patient with a disease. We have historical data of medical records of patients and their diagnosis represented here at the top. And we would use this data, a lot of data, to train a machine learning algorithm. And later on, we would use that machine learning algorithm to and apply it for cases for future patients. And the algorithm would essentially provide us with a prediction on the diagnosis of that particular patient. And since it's sensitive, we would want to ask, why did this algorithm, this probably a black box, gave us this prediction? And here, explainable AI is relevant, and it would give us a set of reasons based on diverse types of approaches for explainability. And with that, we would hope to agree with the decision, or maybe to consider further the uncertainty in the prediction. Now, in this project, we looked at diverse applications and diverse data and diverse machine learning classifiers and explainability methods. And I will not go into each here in this presentation due to lack of time, but I will look at 2 applications we have looked into. One is time series data classification. Now, for time series, in order to perform the classification, typically a representation technique is needed to transform the time series data to a different domain and then perform classification. Now, what we did is, for the sake of explainability, we wanted to use representation techniques that are simple and easy to understand. So to use features that are understandable. And here we use the frequency domain representation and the time frequency domain representation of time series. And we use that for the classification task and later on for the explainability. And so we studied essentially counterfactual explanations is one type of, or one approach for explanations that would quantify the smallest changes starting from a given case. So what would be the smallest changes so that we could change the classifier's decision? And that would help us understand better, okay, that those changes were necessary in order to alter the decision here. Another type of explanation is the feature importance that essentially would quantify the relative importance between the features that actually contributed most to the decision of the classifier. And we studied different types of feature importance methods. One is Sobel's indices, and the other is Shapley values. That's a solution concept from game theory that has a very high influence in the explainability domain, using that game theoretic concept for feature importance. And we depicted that essentially this feature importance, this estimate for the importance of the features is in line with a certain combinatorial problem of finding the smallest set of features that if only those were used would give us high accuracy for classification from that particular classifier. Now, we looked also at applications of explainability where the machine learning classifier also is constructed in a way that would provide privacy guarantees for the participants in the data set. And essentially, if you look at the same illustration as before, now if we would apply a certain privacy mechanism, so we apply differential privacy in order to bring in uncertainty about the presence of certain participants in the data set when the machine learning algorithm is brought out. And now we found out that for those types of classifiers that guarantee certain privacy levels, the explainability, the credibility for explainability is degraded in those applications. And what we did is that we looked in detail into those mechanisms and certain classifier in order to improve that situation. And essentially, we saw that if we could look into the characteristics of the privacy mechanism and the type of machine learning algorithm, we could guarantee certain robustness in the explainability so that we would bring in more confidence that the explanations that we provide are valid to a certain extent. And in more concretely, so we looked at this support vector machine classifier and differential privacy mechanism, and we constructed robust explanations for that setup. And essentially, in this case, we would have a trade-off between the accuracy of classification and the amount of privacy we can guarantee and the validity of explanations. For example, on the left-hand side, we see here the trade-off between the classifier's accuracy and the parameter for privacy here, beta. So lower beta values achieve higher guarantees for privacy, however, at the cost for classification accuracy. We looked also at the trade-off between how much changes are required for counterfactual explanation for that classifier and the level of privacy here, beta, and we see that for higher privacy guarantees, we need to increase the changes necessary in the counterfactual explanation to achieve a fixed amount of confidence that the counterfactual explanation is at a different class according to the classifier. While if we, the same is increasing the amount of changes in the counterfactual explanation is needed when we want to achieve higher confidence levels for the validity of the counterfactual explanation. So this work, we have used that to develop a demonstrator for the project that we also published. And we looked there at synthetic data set where we can sort of change different input parameters and interact with the data set and the explanations and the classifier. And also we applied it for the breast cancer Wisconsin diagnostic data set in that demonstrator. Thank you for listening and see you at Digitalize in Stockholm.